Tonight, we travel to the farthest planet in the solar system, a world so distant, so cold, and so dimly lit that it should be quiet. But Neptune is anything but quiet. It has the fastest winds of any planet, giant storms that appear and vanish, a strange tilted magnetic field, faint broken rings, and a captured moon that may have reshaped its entire system. In many ways, Neptune is not just the farthest planet, it may be the most violent world in the solar system. Before we begin, please take a moment to like the video, subscribe to the channel, and share it with someone who loves space and science. And thank you, as always, for being here and supporting this kind of long-form science storytelling. I'd also love to know what time is it where you are, and which part of the world are you listening from. Please leave a comment below, it's always wonderful to see where everyone is joining from. Now, settle in, and let's begin our journey to Neptune. Long before Neptune became a blue disk in spacecraft imagery, before its storms were named, before its rings and moons were mapped into a larger family, it existed in astronomy as a disturbance, not a sight, not a colour, not even a confirmed point of light, but a quiet problem buried in the motion of another planet. Uranus, newly added to the known architecture of the solar system, refused to behave with complete obedience. Its orbit, once measured against the predictions of celestial mechanics, seemed to drift from where calculation said it should be. The discrepancy was small by ordinary standards, but in astronomy, small deviations have a way of becoming large questions. A planet could not wander for no reason. Either the mathematics was wrong, the observations were wrong, or something unseen was exerting its pull from farther out in the dark. That possibility gave Neptune one of the strangest beginnings of any world in the solar system. Other planets entered human awareness through direct encounter. Mercury and Venus moved in the dawn and evening sky. Mars carried its reddish light across the constellations. Jupiter and Saturn were known since antiquity, slow but unmistakable. Even Uranus, though not recognized as a planet at first, was eventually identified because someone looked at the sky and found an object that did not belong among the fixed stars. Neptune was different. Its existence was argued into being before it was properly seen. It emerged first as an inference, a mathematical necessity, a body that had to be there because gravity had already betrayed its presence. That alone would make Neptune memorable. But the deeper fascination lies in what this episode reveals about the solar system itself. By the 19th century, astronomy had become precise enough that the planets were no longer just wandering lights. They were masses in motion, constrained by equations, each one subtly influencing the others. Newtonian gravity had turned the heavens into a system that could be tested against observation. In such a system, a mismatch was not merely a curiosity, it was evidence. Uranus was tracing a path that seemed to contain an extra hand, one more influence than the known planets could account for. The unseen world beyond it was not discovered by chance. It was extracted from a pattern. Two men working independently, Urbain Le Verrier in France and John Couch Adams in England, followed that pattern toward the same extraordinary conclusion. Starting from the irregularities in Uranus, they attempted an inverse problem of remarkable difficulty. Rather than calculating how a known planet should move under known forces, they tried to deduce the position and mass of an unknown planet from the motion it disturbed. It was a form of celestial reasoning that bordered on audacity. Space beyond Uranus was vast. Observations were limited. Yet the calculations pointed to a particular region of the sky. And when Johann Galle at the Berlin Observatory turned a telescope toward the predicted location, the planet was found astonishingly close to where Le Verrier had said it would be. The moment has often been described as a triumph of mathematics, and it was. But it was also something more delicate than triumph. It showed that gravity could function as a messenger across enormous distance. Neptune, invisible to the naked eye and remote beyond all previously known planets, had already announced itself through motion alone. It had touched Uranus without ever being seen directly. In that sense, Neptune first entered human knowledge not as a world but as an effect. Its reality was felt before it was witnessed. It belonged to a category of discovery that would later become central to modern astronomy, where hidden things are detected through what they do to their surroundings. Long before astronomers inferred black holes from orbiting stars or found exoplanets from the dimming of distant suns, Neptune offered an early lesson in how the unseen can still leave a measurable mark. There is a quiet irony in that beginning. Neptune is now known as a planet of violent winds, dark storms, and a strangely active atmosphere. But the first sign of its existence was almost gentle, a slight mismatch in a planetary orbit, a correction in a table, a point of tension between prediction and reality. The world that would later prove so dynamic began as a discrepancy so subtle that only persistent measurement could reveal it. That contrast matters because it foreshadows something essential about Neptune. Again and again, it turns out to be a place whose outward remoteness hides intense behavior, a planet that seems as though it should be quiet, yet repeatedly refuses that role. Even its naming carried the weight of older patterns meeting new science. Once confirmed, the new planet entered a tradition in which the known worlds of the solar system were linked to mythological figures. Neptune, the Roman god of the sea, was an appropriate choice for a distant blue world, though that blue was not yet truly visible in detail to those who named it. In retrospect, the name seems almost too fitting, not because Neptune resembles a sea in any literal sense, but because it carries the suggestion of depth, motion, and concealed force. It is a name that feels less like ornament than intuition. Yet for all the elegance of its discovery, Neptune remained for a long time more calculation than place. Distance imposed restraint. At roughly 30 times Earth's distance from the Sun, the planet appeared small and faint even through powerful instruments. Through much of the 19th and 20th centuries, astronomers could measure, compare, and refine, but they could not easily see Neptune as a world with detail. It was known to exist, known to orbit, known to perturb and be perturbed, but still withheld its character. This produced a curious imbalance in its history. Neptune was, from the beginning, scientifically respectable. It had been discovered through one of the most intellectually impressive acts in planetary astronomy. But it was not intimate. It remained remote in both senses of the word, far away in space, and difficult to grasp in personality. That gap between proof and familiarity lingered for more than a century. Telescopes improved. Spectroscopy began to reveal broad facts about atmospheric composition. Triton, the large moon discovered soon after the planet itself, hinted that Neptune's system might be stranger than first imagined. But for decades, the planet remained mostly unresolved, a small outer disk carrying more questions than visible answers. There is something fitting in that long delay. A planet first inferred through hidden influence continued to preserve its distance even after discovery. It was present in catalogues, equations, and observatory records, yet still not fully available to direct understanding. When Voyager 2 finally crossed the outer solar system and reached Neptune in the late 20th century, the encounter did not simply add detail to an already familiar place. It transformed the meaning of the planet. What had once been a calculated outer boundary suddenly became a world of dark atmospheric scars, bright clouds, ring arcs, active weather, and a captured moon with a history of disruption. In a sense, there were two discoveries of Neptune. The first was the discovery of its existence. The second was the discovery of its nature. Between them stretched a century of partial knowledge, during which Neptune existed almost in outline, as though the solar system had drawn one of its outermost members in pencil, and only later filled in the force of its expression. That history still shapes the way Neptune is understood today. It is not merely the eighth planet, not merely the farthest major world from the Sun, but a reminder that astronomy often begins with consequences rather than appearances. An object need not announce itself brightly to be real. It can enter knowledge sideways, through perturbation, through imbalance, through a pattern that refuses to close neatly without one more hidden source. Neptune is perhaps the purest planetary example of that principle. Its discovery was not only about finding another world, it was about proving that reason, applied carefully enough, could extend human perception beyond the reach of ordinary sight. And yet the mathematics, impressive as it was, only opened the door. It did not explain what kind of planet waited there. It did not reveal why this distant world would turn out to be so meteorologically violent, so internally active, so unexpectedly alive in motion. It established Neptune as a fact before it was ever understood as an environment. That distinction matters because it gives Neptune's story a rare structure. Most planets are first seen, then interpreted. Neptune was first interpreted, then seen, and only much later truly encountered. From the beginning, it belonged less to the eye than to the hidden architecture of force, and that is where its identity still begins not in brightness, but in the pull it exerts across cold and enormous space. At Neptune, sunlight arrives already diminished into something thin and austere, not absent, but weakened to the point where familiar intuitions about planetary weather begin to fail. The Sun is still the central source of light and order, still the anchor of the solar system, but from this distance it no longer dominates a world in the same intimate way it does nearer in. Neptune circles the Sun at an average distance of about 30 astronomical units, which means it travels roughly 30 times farther from the Sun than Earth does. Expressed in ordinary distance, that is about 4.5 billion kilometers, a scale so large that it begins to resist imagination. Light itself. Moving with a speed that turns most inner solar system distances into brief intervals, takes hours to cross the gulf. A spacecraft launched with modern methods does not arrive in months. It travels for years. The remoteness is not decorative. It is the basic condition from which almost every mystery of Neptune begins. So much of planetary behavior depends on energy received from the Sun that a world this distant ought, at first glance, to seem subdued. The sunlight there is only a tiny fraction of what reaches Earth. Day exists, but under a weaker regime. Warmth exists, but only faintly in the upper atmosphere. The familiar expectation is straightforward. Less solar energy should mean less atmospheric excitement. Gentler contrast, weaker circulation, fewer reasons for a planet to become dynamically expressive. And yet Neptune refuses that expectation so consistently that distance itself becomes part of the puzzle. Before the storms and winds can be understood, the isolation has to be felt properly. Neptune is not merely far. It is far enough that ordinary cause and effect begin to lose their intuitive proportions. That distance also stretches time. One orbit around the Sun takes about 165 Earth years. Neptune was discovered in the 19th century, and humanity has still only observed a little more than a single Neptunian year since that discovery. Entire generations of astronomers pass while the planet completes one slow circuit of the Sun. Seasons unfold there with a patience that barely fits within modern scientific history. On Earth, a season is a passing phase, a familiar change in air, light, and habit. On Neptune, each season lasts roughly 4 decades. A hemisphere can remain in one broad solar condition for a span of time long enough to shape research careers, telescope programs, and the continuity of observation itself. This slows more than climate, it slows certainty. When a planet changes over intervals so extended, no single observer can easily hold its full seasonal rhythm in memory. Even with modern instruments, Neptune is often studied in fragments, each generation adding another narrow slice to a cycle far longer than human attention naturally manages, and still, despite that immense distance and those elongated years, the planet is not inert. Neptune's axis is tilted by about 28 degrees relative to its orbit, not dramatically unlike Earth's own axial tilt. That means Neptune has seasons for the same underlying reason Earth does. Different hemispheres receive changing angles of sunlight across the course of the year. There is nothing conceptually strange in that. What is strange is the scale on which this familiar mechanism has to operate when the sunlight itself is so weak. One might expect that, at Neptune, seasonal differences would be almost trivial, too faint to matter against the planet's cold. But observations suggest otherwise. The southern hemisphere, during its seasonal progression toward greater illumination, has shown measurable changes in brightness and atmospheric behaviour. Even a modest increase in solar input can matter there, not because Neptune is richly heated from above, but because the system appears responsive to small changes layered onto an already delicate balance. That is one of the first hints that Neptune cannot be understood through absolute values alone. The sunlight is weak, but the atmosphere may still react strongly to variations in that weak input. A small change does not always produce a small result when the environment is tuned in the right way. Temperature helps define that environment. Neptune's upper atmosphere is extraordinarily cold, with average temperatures near 200 degrees below zero on the Celsius scale. This is a realm where ordinary materials behave differently, where substances that are gases on Earth can condense, freeze, separate, or descend into deeper layers under changing conditions. Methane, which plays a major role in Neptune's colour and atmospheric chemistry, is especially important here. It absorbs red light and helps give the planet its rich blue appearance. But it is also sensitive to temperature and vertical transport. In colder regions, methane can remain deeper in the atmosphere or condense into hazes and ice particles under the right conditions. In slightly warmer seasonal regions, it may rise more effectively into higher layers. The result is that even the faint sun, operating at extraordinary distance, can still leave visible traces on the planet's appearance. This is not warmth in any comfortable or generous sense. It is narrow adjustment inside profound cold, but on Neptune, narrow adjustments can become planetary scale signatures. The planet's brightness is not evenly fixed. Hemispheres can look different. Clouds can vary. The atmosphere records these subtle imbalances and turns them into evidence. What makes this especially compelling is the contrast between expectation and consequence. At Neptune's distance, solar energy is so reduced that the instinctive assumption is near irrelevance. Yet the evidence says the sun still matters, even there. It matters weakly, but not negligibly. It shapes the timing of seasons. It influences temperature gradients. It affects the behavior of methane and haze. It may help set upper atmospheric conditions that interact with deeper sources of energy rising from below. Neptune is therefore not a planet beyond the reach of the sun, but a planet at the edge of solar authority, where sunlight still exerts influence without being sufficient to explain the whole world. That distinction is crucial. If Neptune were simply dark and still, distance would close the story neatly. Instead, distance opens it. The farther one looks into Neptune's environment, the less satisfying a simple solar explanation becomes. Day and night on Neptune follow another rhythm that deepens the contrast. The planet rotates quickly, completing one turn in about 16 hours. That rapid spin means Neptune is not only remote and cold, but also fast in its own internal timing. A long year contains short days. Seasons unfold with immense slowness, while the planet itself turns briskly beneath its atmosphere. This combination matters because rapid rotation encourages banded circulation and large-scale atmospheric organization. It helps distribute motion into broad east-west flows, shaping the geometry of weather systems. Already, a contradiction begins to take form. Neptune receives little solar energy, but it rotates quickly enough to structure an atmosphere into dynamic patterns. It is cold, yet not motionless. It is distant, yet not detached from seasonal change. It moves through deep time around the Sun while spinning with comparative urgency on its axis. The farther planet begins to look less like a frozen endpoint and more like a place where several incompatible expectations are forced to coexist. Even its visual presence in the solar system reflects this. Neptune cannot be seen with the unaided eye under ordinary conditions. Unlike Mercury, Venus, Mars, Jupiter, and Saturn, it never entered ancient skywatching as a familiar wanderer. It belongs to the telescopic age because its light is too faint and its disk too small. That invisibility has consequences for how it is imagined. Worlds that can be seen easily tend to acquire human familiarity. Neptune remains abstract for longer. It is learned as data before it is felt as place. Yet abstraction can be misleading. The temptation is to treat the outermost giant as a quiet terminal zone, a final blue sphere fading into the dark beyond Saturn and Uranus. But every stable fact about Neptune's distance, year, seasons, and weak sunlight only sharpens the coming contradiction. A planet this far from the Sun should not seem energetically expressive enough to become the most violent weatherworld among the major planets. It should not, by simple intuition, support winds that outrun those on Jupiter and Saturn. It should not sustain dark storms and bright cloud activity with such force. And yet it does. The edge of sunlight is not the end of Neptune's story. It is the point where the story becomes difficult. The cold establishes the setting. The long year stretches the rhythm. The tilted axis introduces seasonal asymmetry. The weak sun still leaves fingerprints. But none of that fully explains why Neptune feels in motion. More intense than a world at the frontier of solar warmth has any clear right to be. By the time, distance, temperature, and time have all been accounted for, the central fact remains standing more sharply than before. Neptune is too far from the Sun to be this alive, and that is precisely why it demands a deeper look. Neptune's blue is often the first thing remembered about it, but the colour is not a surface feature in any ordinary sense. It is not paint, not ocean, not stone, not a shell wrapped around the planet like a visible skin. It is the appearance of an atmosphere several thousand kilometres deep, an optical effect produced by chemistry, light, altitude, and the layered structure of a world that has no solid outer ground to stand upon. That distinction matters because Neptune is easy to simplify from a distance. Seen through telescopes or in familiar spacecraft images, it can seem like a smooth blue sphere set quietly at the edge of the solar system, serene in outline, almost minimal in its design. But that clean disk is deceptive. What looks simple from far away is, on closer inspection, a stratified and active planetary envelope, with gases, hazes, clouds, and temperature gradients stacked into a system that both reveals and conceals the deeper world beneath. To understand why Neptune looks the way it does is to begin understanding why it behaves the way it does. The blue is not merely decorative, it is the visible expression of atmospheric physics. The outer atmosphere of Neptune is made mostly of hydrogen, with helium forming much of the remainder, and methane present in a smaller but critically important amount. Hydrogen and helium dominate by abundance, yet they do not define the planet's colour in the human eye. Methane does. When sunlight reaches Neptune and reflects back through its atmosphere, methane absorbs red wavelengths more strongly than blue ones. The light that escapes upward therefore carries more of the blue part of the spectrum, and the planet takes on its characteristic appearance. The process is simple in principle, but on Neptune it is shaped by depth and layering. Light does not merely touch a thin shell and bounce away. It passes through a column of gas, haze, and cloud, interacts with particles at different altitudes, and returns altered. That is why Neptune's blue is not the pale blue of a clear sky on Earth, and not the cyan tint often associated with Uranus. It is darker, richer, more saturated, as though the atmosphere holds both light and shadow within the same colour. For a long time, methane alone was treated as the main explanation for the contrast between Uranus and Neptune, since both planets contain methane and both appear blue. But the difference in shade suggests that methane is not the whole story. The broad understanding now is that upper atmospheric haze also matters. Uranus appears somewhat lighter because its atmosphere may contain a more substantial haze layer that mutes the deeper blue beneath, while Neptune's atmosphere, being more dynamic, may keep some of that haze thinner or more disrupted in places, allowing a more vivid blue to remain visible. The difference is subtle, but it points to an important idea. Colour on a planet is not only about composition, it is also about motion, mixing, and the vertical arrangement of particles. Neptune's blue is therefore a sign not just of methane, but of an atmosphere organised in a particular way. What seems like a visual identity becomes, on inspection, a clue to process. Above all, Neptune is an atmosphere before it is anything else that can be directly known. Unlike Earth or Mars, there is no familiar surface at the top of the planet's visible form. The upper clouds mark a transition in opacity, not a firm boundary between sky and ground. Descend through the visible atmosphere and the pressure rises steadily. The gases become denser, warmer, and stranger in behaviour. What begins as an atmosphere grades downward into fluids under immense compression. The convenient categories of gas, liquid, and solid become less intuitive there because temperature and pressure push materials into regimes far from everyday experience. Even the phrase ice giant can mislead if taken too literally. Neptune is grouped with Uranus as an ice giant because its interior contains larger proportions of substances such as water, ammonia, and methane than Jupiter and Saturn do, not because it is made of simple frozen ice in the ordinary sense. Deep inside Neptune, these materials are not sitting in neat cold layers like stacked winter deposits. They are thought to exist in hot, dense, high-pressure forms, possibly mixed into a convecting mantle that behaves more like an exotic fluid than a quiet reservoir. The atmosphere above that hidden interior is arranged into layers that differ in temperature and behaviour. The troposphere is the lowest region of the atmosphere that can still be thought of in atmospheric terms, the domain where temperature generally changes with height and where much of the visible weather takes shape. This is where methane clouds can form under the right conditions, where rising and sinking motions help organise the planet into bands and storms, and where the visible face of Neptune is continuously assembled and erased. Above the troposphere lies the stratosphere, thinner and more rarefied, where sunlight interacts with gases in different ways and where temperature behaviour can reverse because of absorption processes. Still higher layers continue upward into the more tenuous extremes of the atmosphere. But for understanding Neptune's appearance, the troposphere and stratosphere do much of the visible work. They are the levels in which chemistry becomes colour and motion becomes pattern. Even that layering should not be imagined as a calm stack of static shells. Neptune's atmosphere is not quietly sorted, it is stirred. Material can be lifted from below, transported sideways, cooled, condensed, warmed, and redistributed across latitude and altitude. This constant rearrangement is one reason the planet can change in brightness and cloud structure over time. High-altitude methane ice clouds can appear as bright features against the darker blue background, sometimes stretched into bands, sometimes gathered into compact patches, sometimes trailing the larger storms that churn through the deeper atmosphere beneath them. These clouds are often compared, in visual effect, to thin white brush strokes laid across a blue sphere. But even that image is gentler than the underlying process deserves. Their brightness reflects sunlight efficiently, yet their existence depends on upward motion and atmospheric contrast. They are not passive ornaments. They are markers of a restless system. The deeper one goes, the less Neptune resembles any common image of a planet. Beneath the atmosphere lies the mantle region, rich in water, ammonia, and methane under tremendous pressure. Beneath that is a dense core, likely rocky and metallic in broad composition, though exact structure remains uncertain. No probe has descended through these layers. No instrument has directly sampled the deep interior. Neptune's structure is inferred from mass, radius, gravity measurements, magnetic behavior, models of planetary formation, and laboratory work on matter under extreme conditions. In that sense, the visible atmosphere is not only the planet's face, it is also the main accessible record of what lies below. The weather, the colour, the brightness, and the circulation all carry partial information upward from a hidden interior that remains beyond direct reach. Neptune therefore has a peculiar identity among planets. It looks smooth, but it is layered. It looks simple, but it is chemically selective. It looks cold, but it sits above a much warmer and denser interior. It looks distant and self-contained. Yet the appearance of its atmosphere depends on a balance between faint sunlight from above and internal energy from below. The planet's blue, which might seem the easiest fact about it, becomes a gateway into almost every major question about the world. Why is the haze distributed as it is? How efficiently are gases mixed upward from depth? How do temperature and circulation shape cloud formation? Why does Neptune differ visibly from Uranus if the two planets are so similar in broad composition? These are not decorative questions, they are structural ones. The visible colour is where chemistry, climate, and hidden dynamics meet. That is why Neptune's appearance cannot be separated from its mystery. The disk seen from afar is not the whole planet, but a moving atmospheric boundary where light encounters matter and returns with only part of the story. The deeper world remains concealed by pressure, distance, and the difficulty of direct exploration. Yet the atmosphere offers enough hints to make Neptune more than a remote blue point. It is a layered planetary environment, one in which colour is evidence, clouds are signals, and the very look of the planet tells of selection, absorption, and motion. What emerges from that blue is not calm simplicity, but a carefully disguised complexity. A world whose visible identity is produced by processes still unfolding through great depth. Once that is understood, Neptune no longer appears as the last quiet sphere in the solar system. It appears as an atmosphere with an entire planet hidden inside it. Along Neptune's equator and across its middle latitudes, the atmosphere does something that still feels out of proportion to its place in the solar system. It accelerates into winds that can exceed 2,000 kilometers per hour, fast enough to outrun the most violent large-scale atmospheric flows on any other major planet. That fact is easy to state and much harder to absorb. Jupiter is larger, more massive, and more obviously dramatic in appearance. Saturn carries its own banded atmosphere and immense storms. Even Earth, on the small scale of human weather, can produce tempests of extraordinary local force. Yet Neptune, farther from the sun than all of them, colder than intuition can easily tolerate, and receiving only a small fraction of the solar energy available to the inner planets, drives the fastest sustained winds in the solar system. The problem is not simply that Neptune is windy. The problem is that it is windy in a place where the ordinary budget of atmospheric energy seems too meagre to justify such speed. This is where Neptune stops being merely remote and starts becoming physically difficult. Wind on a planet is never just air in motion. It is the atmosphere responding to gradients, to differences in temperature, pressure, rotation, chemistry, and energy flow. Somewhere in the system there must be contrast, and where contrast exists, fluid motion follows. On Earth, much of that contrast comes from uneven solar heating. The equator receives more energy than the poles. Oceans, land, and atmosphere exchange heat unevenly. Weather becomes the atmosphere's effort to redistribute imbalance. On the giant planets, the picture is more complex, but the principle remains recognizable. Atmospheric motion requires a source of structure. Pressure differences must be built. Vertical movement must be fed. Rotation must organize the resulting flow into long bands and vortices. The question on Neptune is not whether those processes exist, it is why they're so effective under such weak sunlight. Voyager 2 offered the first close view of this paradox in action. When it passed Neptune in the late 20th century, the spacecraft did not find a quiet outer giant fading into thermal exhaustion. It found a planet alive with bands, streaks, bright clouds, and large dark storms. More than that, the motions of these features allowed wind speeds to be estimated, and the results were startling. Neptune's atmosphere was racing. Some flows moved westward relative to the planet's rotation near the equator, while other bands at higher latitudes took on different directions. The atmospheric circulation was not random, but strongly organized, divided into zonal jets that wrapped around the world. These are broad east-west flows shaped by the planet's rapid rotation. And on Neptune they reach remarkable intensity. The equatorial jet in particular is strongly retrograde, meaning it moves opposite to the direction of the planet's spin. Other regions host prograde motion, creating a pattern of alternating belts of circulation, whose details still carry uncertainty because Neptune is so difficult to monitor continuously. Even so, the broad message has remained stable. The atmosphere is not merely active in isolated storms, it is globally energetic. What makes the winds especially compelling is that they do not announce themselves through a permanently dramatic surface pattern, in the way Jupiter's atmosphere does. Neptune's visible cloud features can be sparse by comparison. Much of the planet can look relatively smooth from a distance, a deep blue sphere with only occasional bright markings and dark disturbances. That visual restraint can be misleading. A world does not need to show constant visual turbulence everywhere in order to sustain powerful winds. In fact, the relative simplicity of Neptune's appearance makes the violence of its atmospheric motion more striking. The speed is not obvious at first glance. It has to be inferred from the movement of clouds and storms across time, from the drift rates of features, from the repeated observation of a planet that reveals its force only when watched carefully. The atmosphere, in that sense, hides its own intensity beneath a cleaner face. Rotation is part of the explanation. Neptune spins quickly, completing a full rotation in about 16 hours. Rapid rotation encourages the development of zonal jets because moving air is strongly influenced by the Coriolis effect, which deflects large-scale flow and helps organize it into long belts rather than allowing simple poleward and equatorward exchange. This is one reason all 4 giant planets show banded atmospheric structures to some degree, but rapid rotation alone does not explain why Neptune's winds are so much faster than Uranus's. Uranus also rotates quickly. It also has hydrogen, helium, and methane in its atmosphere. It also occupies the cold outer solar system. Yet Uranus appears more subdued in its visible weather and does not approach Neptune's most extreme wind speeds. That comparison sharpens the question. The relevant puzzle is not only why Neptune is active, but why Neptune is more active than its nearest planetary relative. Clouds provide another clue. Bright methane ice clouds appear at high altitude on Neptune, often associated with rising motion from deeper layers. Some can change quickly over surprisingly short timescales. They are not the winds themselves, but they act as tracers, visible markers suspended within the larger circulation. By watching how these clouds form, stretch, and drift, astronomers glimpse the architecture of motion underneath. In some cases, the bright clouds are connected to deeper storm systems, likely produced as air is forced upward and cools, allowing methane to condense. In others, they appear more transient, shaped by local instabilities or wave activity moving through the atmosphere. Their behavior suggests that Neptune's atmosphere is not just fast in the horizontal direction, it is vertically active as well, with rising and sinking regions helping convert hidden energy into visible structure. This matters because strong winds are easier to sustain when the atmosphere is being fed from below as well as organized from above. The visible bands and clouds imply a system in which motion is continually refreshed. Even the distribution of winds on Neptune resists overly simple expectation. Near the equator, the strong retrograde flow stands out as one of the planet's defining features. But the atmosphere at higher latitudes behaves differently, with other jets moving in the opposite direction. The result is not one single planetary wind, but a pattern of alternating currents wrapped around a rotating sphere. Neptune is therefore less like a planet with one dominant gale, and more like a world whose atmosphere has settled into a global arrangement of high-speed pathways. Within that arrangement, storms can form, dark vortices can drift, and bright clouds can trail behind the deeper circulation. The violence is structured rather than chaotic. That may be why Neptune feels so scientifically unsettling. A random outburst could be dismissed as episodic. A system of organized jets suggests something more fundamental. A persistent engine operating under conditions that still seem insufficient by solar reasoning alone. One possible temptation is to assume that Neptune's atmosphere must simply be a scaled-down version of Jupiter's or Saturn's, driven by the same broad principles but expressed under colder conditions. There is some truth in the comparison, but it risks hiding the peculiarity of Neptune's case. Jupiter and Saturn are larger, richer in internal heat overall, and visibly more expansive in their cloud architecture. Neptune is smaller, dimmer, and farther. It should, by naive expectation, be more sluggish. Instead, it compresses extraordinary atmospheric performance into a more compact and distant world. The same basic physics of rotation and fluid dynamics apply, but the outcome is not merely familiar. It is exaggerated in a direction that makes explanation harder rather than easier. That is why the winds matter so much. They are not just one interesting fact among many. They are the sharpest expression of Neptune's defiance. Every kilometre per hour added to those jet speeds increases the pressure on theory. The atmosphere is telling astronomers that somewhere inside the planet, or in the structure of its radiative balance, or in the way its gases and temperature gradients interact, there exists a more effective mechanism for driving motion than distance from the Sun would suggest. The evidence does not yet resolve that mechanism fully, but it removes the comfortable option of treating Neptune as a cold world whose weather is merely residual. Its winds are too fast for that. They force a reinterpretation of the outer solar system, where weakness of sunlight does not necessarily mean weakness of climate. On Neptune, the atmosphere does not merely endure the cold, it uses the planet's hidden contrast to race through it, turning remoteness into one of the most powerful meteorological expressions in the solar system. Once that is clear, the next question becomes unavoidable. If the winds are this strong, what kinds of storms can a world like this actually sustain? And why do some of them appear only to vanish again into the blue? When Voyager 2 approached Neptune in the late 1980s, one feature immediately disrupted any lingering idea that the planet might be meteorologically restrained. Set against the deep blue atmosphere was a vast dark oval in the southern hemisphere. Large enough to rival Earth in scale and sharp enough in contrast to suggest a coherent atmospheric structure rather than a vague stain in the clouds. It came to be known as the Great Dark Spot, and in the first close views of Neptune it carried much of the same visual authority that Jupiter's Great Red Spot had long held in the imagination. Here, at the edge of the solar system, was a storm with planetary scale, visible proof that Neptune's atmosphere could organize itself into giant rotating systems of extraordinary size. Yet the resemblance to Jupiter's famous storm turned out to be misleading. Neptune's great dark vortices are not monuments of endurance. They are episodes. They form, evolve, drift, and disappear. Their importance lies not in their permanence, but in their refusal to stay. The Great Dark Spot was accompanied by something else that helped define Neptune's atmospheric character. Nearby bright clouds appeared at higher altitude, likely composed of methane ice, trailing or bordering the darker system below. These white features did not simply decorate the storm. They revealed vertical structure. Beneath them, a deeper vortex was influencing air motion strongly enough to force gases upward, where cooling allowed condensation into bright cloud tops. The dark storm and its companion clouds therefore represented two levels of the same atmospheric event. One marked a rotating disturbance deeper in the atmosphere. The other showed the atmosphere's visible response above it. This combination made Neptune's storm scientifically rich. They were not only shapes to be tracked across the disk. They were windows into how motion moves through depth on a planet with no solid surface and only indirect access to its hidden layers. Voyager also identified a smaller dark storm farther south, commonly called the Small Dark Spot, along with a bright, fast-moving cloud feature sometimes nicknamed a scooter because of how quickly it traversed the atmosphere. Together, these features gave Neptune a face of startling variety. It was not just windy, it was structured by large, coherent vortices, streaked by high clouds, and animated by systems that seemed at once organized and unstable. At that moment, a natural comparison arose. Perhaps Neptune possessed its own long-lived giant storm, an outer solar system counterpart to Jupiter's centuries-old vortex. Perhaps the Great Dark Spot was a fixed feature of the planet, an enduring engine embedded in a persistent band of circulation. That would have been dramatic, but it would also have been comparatively easy to understand. A permanent storm becomes part of the planet's stable identity. Neptune offered something less comfortable. When the Hubble Space Telescope later examined the planet, the Great Dark Spot was gone. It had vanished. The enormous storm seen by Voyager 2 did not remain in place as a lasting landmark. It did not survive as a visible fixture to be revisited decade after decade. Instead, it disappeared into the very atmosphere that had created it, leaving behind not resolution, but a more difficult question. What kind of planet produces storms of that scale only to erase them again on relatively short timescales? Hubble would go on to show that Neptune was still capable of generating new dark vortices. Other storms appeared in later years, often at different latitudes, sometimes accompanied by bright clouds, sometimes changing shape, drifting, or fading as astronomers tried to follow them. This established a new picture of Neptune's violence. The storms were real, powerful, and recurring, but not fixed. Their world was one of formation and decay rather than endless survival. That difference separates Neptune sharply from Jupiter. Jupiter's Great Red Spot is a long-lived anticyclone embedded within a broad and comparatively stable atmospheric system. However much it may change in size and colour over time, Neptune's dark spots, by contrast, seem to belong to a more transient family. They are giant vortices, but their lifespan appears measured in years rather than centuries, and their migration through latitude may contribute to their destruction. A storm on Neptune can grow large enough to dominate the visible planet, and still prove temporary in the larger rhythm of atmospheric life. That impermanence is not a minor detail. It may be one of the most revealing facts about Neptune's climate. A storm that endures for centuries suggests one balance of forces. A storm that forms and dies comparatively quickly suggests another. Neptune's atmosphere seems able to create large vortices efficiently, but not always to preserve them. The reasons are still being worked through, but several possibilities shape the current understanding. Dark spots on Neptune are thought to be high-pressure systems, likely anticyclonic vortices, embedded within the broader zonal winds of the atmosphere. Their dark appearance may come from differences in aerosol distribution, cloud altitude, or the clearing and rearrangement of atmospheric particles compared with surrounding regions. They are not holes in the simple sense, but regions where the local atmospheric structure changes the way light is scattered and absorbed. Their edges interact with the surrounding flow, and their movement across latitude may expose them to changing wind shear, meaning the atmosphere around them stretches and distorts them differently depending on where they travel. A vortex that moves away from the latitude range most favourable to its stability may begin to weaken, deform, or fragment. In that sense, Neptune's storms may be not only born from the broader circulation, but also eventually destroyed by it. Observations have hinted at exactly this kind of atmospheric vulnerability. Some dark spots appear to migrate toward the equator, a region where planetary vortices may become less stable because the Coriolis effect, which helps organize rotating systems, weakens there. Others may break apart under the strain of surrounding currents, or lose coherence when the vertical structure that supports them is disrupted. Bright companion clouds can also change quickly, appearing and fading on shorter timescales than the deeper storm itself. The visual life of a Neptunian storm is therefore layered in time. The underlying vortex may persist for a while. The bright clouds above it may come and go much faster. The whole system may drift into a region of the atmosphere where its survival becomes harder. The result is a planet whose visible weather is not simply violent, but narratively unstable. Features arrive with force, hold attention briefly, and then disappear, sometimes leaving only new questions behind. That instability makes Neptune unusually dependent on long-term observation. A spacecraft flyby can reveal astonishing structure, but a single encounter cannot establish what belongs to the planet's permanent climate and what belongs only to a passing phase. Neptune's dark storms taught astronomy exactly that lesson. Voyager revealed the phenomenon, Hubble revealed its transience. Continued observations then showed recurrence without permanence. This is a deeper kind of mystery than a single unexplained storm would have provided. It means Neptune's atmosphere is not organized around one great stable feature, but around a capacity for repeated large-scale disruption. The violence is renewable. It does not need to reside in one immortal vortex. It can arise again from the planet's broader circulation, as though the atmosphere periodically gathers itself into concentrated rotating systems and then releases them back into the blue. Even the contrast between dark vortices and bright clouds carries a distinctive emotional tone in Neptune imagery. The dark storms look like absences, as though something has been removed from the planet rather than added to it. Yet they are signs of active atmospheric structure. The bright clouds, by contrast, appear almost delicate, thin and reflective, while actually recording energetic uplift and rapid change. Neptune repeatedly reverses visual intuition in this way. Darkness can mean organized motion. Brightness can mean turbulence. A smooth blue globe can conceal short-lived systems as large as Earth. This is why the storms matter beyond their immediate spectacle. They show that Neptune's atmosphere is not only fast, it is capable of assembling giant coherent features and then dismantling them, all within a climatic regime still not fully explained. The data does not end the mystery, it changes the shape of it. The question is no longer whether Neptune can sustain major storms, it plainly can. The deeper question is what hidden balance of internal heat, atmospheric stratification, rotation, and chemistry allows those storms to be born so forcefully and yet remain so temporary. Their disappearance is not a failure of explanation but part of the evidence itself. On Neptune, violence does not settle into permanence. It passes through the atmosphere like a recurring event, large enough to remake the visible planet for a time, unstable enough to leave no single storm behind as its final signature. Of all the comparisons in the outer solar system, few are as revealing as the one between Neptune and Uranus, because no other pair of planets look so similar at first and behave so differently once observed closely. Both are classed as ice giants. Both are made mostly of hydrogen and helium in their outer atmospheres, with methane helping tint them blue. Both are smaller than Jupiter and Saturn, yet far larger than Earth. Both carry deep mantles rich in water, ammonia, and methane in forms shaped by immense pressure rather than ordinary cold. Both rotate quickly. Both possess tilted, unusual magnetic fields. From a distance, they appear almost like variations on the same planetary design, one somewhat paler, the other darker and deeper in colour. If composition and size alone determined atmospheric personality, Uranus and Neptune might be expected to resemble one another closely. Instead, they offer one of the clearest reminders that planets are not defined by ingredients alone, but by energy, history, and the ways internal structure either releases or traps what was built into them long ago. Neptune is the more distant of the two, farther from the sun, colder in setting and weaker in sunlight. By simple expectation, it should be the quieter world. Uranus, slightly nearer the sun and broadly similar in composition, ought to be at least as active and perhaps more so. But the opposite is true. Neptune drives the faster winds, the more dramatic storms, the stronger cloud contrasts, and the more visibly restless atmosphere. Uranus can certainly be active, and modern observations have shown that it is not the completely featureless sphere it was once assumed to be, yet it still does not match Neptune's atmospheric intensity. This is not a small mismatch between theory and observation. It is one of the major clues to how these planets work. The broad explanation begins with heat, not the heat they receive from the sun, but the heat they release from within. Neptune radiates significantly more energy into space than it receives from sunlight alone. Uranus, by contrast, emits remarkably little excess internal heat. That difference may be the single most important reason Neptune appears meteorologically alive while Uranus so often seems comparatively restrained. A planet's atmosphere does not need sunlight alone to move. If energy is rising from the interior, it can drive convection, meaning warmer material rises and cooler material sinks, creating vertical exchange that feeds weather and helps power winds. On Neptune, that internal contribution appears substantial enough to matter. On Uranus, it appears unexpectedly weak. The significance of this contrast is difficult to overstate. Two planets can share similar mass, similar broad composition, and even similar outer atmospheric chemistry. Yet if one is leaking internal energy more effectively than the other, their climates may diverge sharply. Neptune may simply have a stronger engine beneath its clouds. That idea does not solve everything. but it changes the problem from a mystery of outer appearance into a mystery of planetary history and structure. Why would Uranus retain so little accessible heat, while Neptune continues to release it? Why would two neighbouring planets, likely formed in comparable regions of the early solar system, end up with such different internal behaviour? One possibility often raised is that Uranus suffered a colossal impact early in its history, perhaps from an object roughly Earth-sized. Such an event is already invoked to help explain Uranus's extreme axial tilt, which causes the planet to rotate almost on its side relative to its orbit. A collision of that magnitude could also have rearranged the planet's interior in ways that matter today. Instead of simply adding heat, it may have left Uranus with a layered internal structure that suppresses efficient convection. If internal material became stratified, with composition gradients resisting vertical mixing, then heat from deeper layers might have more difficulty escaping upward. The planet would still contain energy, but it would be trapped more effectively, unable to feed the atmosphere above with the same freedom Neptune seems to enjoy. This idea remains a model rather than a settled fact, but it is attractive because it links Uranus's odd tilt and weak heat flow into one larger story. Neptune, in this picture, may be less extraordinary than Uranus. It may be the more normal ice giant, continuing to vent primordial heat left over from formation, while Uranus is the disrupted one, its interior altered in a way that dampens atmospheric vigour. Even so, Neptune is not merely normal in any simple sense. Its winds are still extreme, and its climate still produces large storms that appear and vanish on timescales shorter than expected. Internal heat helps explain why Neptune can outperform Uranus meteorologically, but it does not by itself account for all the details. What it does provide is a stronger physical basis for the contrast. Uranus receives slightly more sunlight than Neptune, yet Neptune's atmosphere is more dynamic. Therefore, the crucial energy source is unlikely to be sunlight alone. Something internal must be tipping the balance. Once that is accepted, the differences between the two planets begin to look less like cosmetic variations and more like evidence of two distinct thermodynamic regimes hiding inside superficially similar worlds. Colour even becomes part of that distinction. Uranus appears lighter, often with a more muted cyan tone, while Neptune presents a darker blue. Methane exists in both atmospheres, so the difference likely depends not only on composition, but on how material is mixed vertically and how haze is arranged in upper layers. A more active atmosphere on Neptune may keep certain haze layers thinner or redistribute aerosols in ways that allow the deeper blue to show more clearly. Uranus, with weaker internal stirring, may sustain a more uniform or more optically muting upper haze. In that sense, the visible difference between the two planets may be another surface clue to a deeper energetic difference. The planets do not only behave differently, they look differently because they may be moving their atmospheres differently. Seasonal geometry complicates the comparison further. Uranus has an axial tilt so extreme that its poles can point almost directly at the Sun during parts of its orbit, producing unusual seasonal patterns unlike those on any other major planet. Neptune's tilt, though significant, is much more moderate and more Earth-like in broad effect. At first glance, one might suspect that Uranus's extraordinary seasonal extremes should generate abundant atmospheric drama. Yet the observational record has often shown otherwise, at least in comparison with Neptune's baseline activity. Uranus does show seasonal changes and occasional storms, particularly as sunlight returns to different hemispheres over long intervals, but its overall weather still seems less continuously forceful. This again supports the idea that sunlight, while important, is not the sole master variable. Atmospheric violence depends not only on how energy arrives from above, but on whether the planet is also feeding motion from below. Neptune seems to do both more effectively. There is also the matter of how each planet uses whatever energy it has: internal structure, atmospheric stability, cloud condensation levels, and the efficiency of heat transport all influence whether available energy becomes visible weather or remains hidden in more quiescent layers. Neptune may be better at converting internal heat into atmospheric motion. Uranus may either possess less available outward heat, or may distribute it in ways that do not produce equally dramatic large-scale circulation in planetary science. This is often the most difficult distinction to settle. Two worlds may differ not in the existence of energy, but in the pathways that energy is allowed to follow. A trapped interior and a freely convecting interior can create atmospheres with very different personalities, even when the planets appear otherwise related. The deeper value of the Neptune-Uranus comparison lies in what it says about planetary classification itself. Labels such as ice giant are useful, but they can easily become too blunt. They suggest a family resemblance, and that resemblance is real. Yet they also risk implying a uniformity that the planets do not possess. Neptune and Uranus are siblings, but not twins in climate. One presents itself as a world of fast jets, dark vortices, and strong internal expression. The other, though far from inert, often appears more sealed, more muted, more reluctant to convert its deep past into visible meteorology. This difference may trace back to ancient accidents of formation, giant impacts, internal layering, or the long thermal evolution of each planet over billions of years. Whatever the full explanation proves to be, the contrast has already done something important. It has turned Neptune's violence from an isolated curiosity into part of a controlled comparison. Neptune is not merely active in absolute terms, it is active relative to the most obvious planet with which it should be compared, and in that comparison Neptune repeatedly wins. That is why Uranus matters so much to Neptune's story. Without Uranus, Neptune would simply seem unusual. With Uranus beside it, Neptune becomes diagnostic. It shows what an ice giant can do when internal heat remains available to the atmosphere. It shows how profoundly two similar worlds can separate once energy flow begins to diverge. And it suggests that the true source of Neptune's violence is not visible in the clouds alone, but buried deeper, in a hidden interior that has somehow remained more willing to release its strength into the cold above. Pressure begins to matter on Neptune long before any imagined descent reaches what could reasonably be called the deep interior. There is no firm surface waiting beneath the blue, no simple boundary where atmosphere ends and ground begins. Instead, the planet thickens. Gas becomes denser, temperature rises, and the familiar categories used for matter near Earth begin to lose their clarity. The upper clouds, dramatic as they are, belong only to the outermost expression of a much larger structure hidden below. Neptune's weather does not arise over rock and ocean in the terrestrial sense. It is generated above an interior that grades from atmospheric layers into compressed fluid regions, and then downward again toward a dense core, with each step inward increasing the pressure to levels difficult to reproduce and even harder to imagine. This is where the visible violence of Neptune begins to look like the surface symptom of something deeper, because the atmosphere above may owe much of its restless power to heat, motion, and chemistry unfolding far beneath the clouds. In broad outline, Neptune is thought to consist of three main regions. There is the outer atmosphere, composed mostly of hydrogen and helium, with methane playing an outsized role in appearance and cloud formation. Beneath that lies the mantle, a vast region rich in water, ammonia, and methane under enormous pressure and temperature. At the centre sits a dense core, likely made of rock and metal in broad compositional terms, though its exact size and internal arrangement remain uncertain. This layered description is useful, but it should not be mistaken for a neat stack of familiar materials. Neptune is not built like a sequence of ordinary substances placed one above another in recognizable states. The mantle, for example, is often described as icy. Yet deep inside Neptune, these so-called ices are not frozen in the everyday meaning of the word. They are hot, dense, and compressed into exotic forms, moving under conditions where the distinction between liquid, solid, and superheated fluid becomes far less intuitive than the labels suggest. What matters here is not the name of the layer, but the regime it represents. Neptune's interior is a place where common molecules are forced into uncommon behavior. The planet formed early in solar system history from gas, ice-rich material, and heavier elements gathering around a growing core. That formation process left behind heat, both from the energy of accretion and from the compression of the planet under its own gravity. Over billions of years, a planet radiates some of that internal energy away. But not all worlds do so at the same rate or with the same efficiency. Neptune still releases substantial heat into space, more than it receives from sunlight alone, and that internal heat appears to be one of the main reasons its atmosphere remains so active. The significance of this is easy to miss because the planet looks so cold from the outside. The upper atmosphere is indeed frigid, but the cold visible top of Neptune is not the whole thermal story. A world can be cold at its outer edge and still retain a stronger interior energy source than its appearance suggests. Neptune seems to be exactly that kind of world. Deep below the visible clouds, temperatures climb sharply. Pressure climbs even faster. Matter responds by entering states that are not directly observed but inferred through a combination of planetary models, laboratory experiments, and the measured mass, radius, gravity field, and heat output of the planet itself. In the mantle region, water, ammonia, and methane are thought to form a hot, dense fluid mixture, perhaps convecting in large, slow currents that carry energy upward. Convection is one of the most important ideas here. If deeper regions are warmer and less dense than the material above them, they can rise, while cooler material sinks in return. Over vast scales and immense times, this process becomes a planetary heat engine. On Earth, convection occurs in the mantle and atmosphere under very different conditions. On Neptune, convection may operate through layers of electrically conducting and chemically unusual fluid, transporting heat from the deep interior toward the atmosphere above. The details remain uncertain, but without some version of that vertical energy transport, it becomes much harder to explain why Neptune's atmosphere is as vigorous as it is. This is where the hidden and visible parts of the planet begin to join. The winds and storms seen from space are not disconnected from the interior. They may be the uppermost consequences of a heat flow that has been climbing through the planet for billions of years. The most striking possibilities emerge where methane is carried into regions of extreme pressure. Under sufficiently intense compression, methane molecules may break apart, releasing carbon from its molecular bonds. In principle, that carbon could then be forced into crystalline forms. This is the origin of the famous idea that diamonds may form deep within Neptune. The phrase, diamond rain, has become one of the most memorable images associated with the ice giants, partly because it is vivid, and partly because it sounds almost too ornate to belong to real planetary science. Yet the underlying concept is not fantasy in its basic physical logic. High-pressure experiments and theoretical work suggest that carbon-rich compounds under conditions like those inside Neptune can indeed separate and reorganize into denser structures. Whether this produces literal rain of diamonds in the simple pictorial sense is less certain. The deeper reality is probably more complex, involving gradients of pressure, temperature, dissolution, growth, and movement through hot, dense fluid. Still, the idea captures something important. Neptune's interior may be chemically active in ways that turn familiar molecules into entirely different materials, all under conditions where the products of that transformation then move through the planet's deeper layers. Even without leaning too heavily on the most dramatic version of the concept, the larger truth remains remarkable. Neptune may contain regions where carbon chemistry leaves the ordinary world behind. Pressure near the core is expected to reach millions of times the atmospheric pressure at Earth's surface. Under such conditions, the behavior of matter becomes an experimental frontier as much as an astronomical one. Water itself may no longer resemble any familiar liquid or ice. Some models suggest that in parts of Neptune and Uranus, water-rich material could enter a supersonic state, in which oxygen atoms form a lattice while hydrogen ions move through it more freely, producing a phase that is neither standard liquid nor ordinary solid. This matters not only because it is exotic, but because electrically conductive layers deep inside Neptune may help generate its unusual magnetic field. The interior is therefore not only a reservoir of heat, it may also be part of the machinery that creates the planet's tilted and offset magnetism. The deeper one looks conceptually into Neptune, the less it behaves like a distant version of a simpler planet, and the more it appears as a world shaped by states of matter that barely exist anywhere in ordinary human experience. Yet the interior is not important only for its strangeness. It is important because it may explain the atmosphere above. A planet that releases internal heat can sustain stronger vertical motion. Stronger vertical motion can help feed cloud formation, reinforce temperature contrasts, and contribute to the circulation that produces Neptune's extraordinary winds. Internal heat does not act alone. Rotation, atmospheric composition, radiative balance, and cloud microphysics all matter as well. But without the upward energy source from within, the planet's meteorology would be much harder to maintain at the observed intensity. Neptune's violence may therefore begin in silence, in the long steady leakage of primordial and gravitational heat through a deep mantle no eye will ever see directly. There is a certain dignity in that hidden engine. The most turbulent visible features of Neptune may owe their existence to processes unfolding under such pressure that language begins to rely on approximation. No spacecraft has entered those depths. No image shows the mantle. No direct sample confirms the exact behavior of carbon, water, or ammonia at each level. Much of the interior remains a model stitched together from the outside inward, a physical argument built from what the planet does reveal. And yet the broad picture has force. Neptune is not only a cold atmosphere under faint sunlight, it is a warm interior wrapped in cold distance. A planet still giving off more of itself than its location would seem to allow. That may be why it feels so contradictory. The father planet turns out not to be thermally exhausted, but internally expressive. Beneath the blue lies compression. Beneath compression lies rearranged chemistry. And beneath the storms lies a heat source still working its way upward. By the time that hidden energy reaches the visible atmosphere, it has been translated into motion, cloud, and wind. The cold remains real, but it is no longer the dominant fact. The deeper fact is that Neptune carries an engine beneath the ice-rich mantle, and that engine may be the quiet origin of almost everything that makes the planet seem impossible. When Voyager 2 crossed Neptune's magnetic environment, the surprise was not that the planet had a magnetic field at all, but that the field behaved as though it did not fully belong to the planet's visible symmetry. On a simple world, or at least on a world simple enough to satisfy first expectations, a magnetic field might emerge neatly from near the centre and align itself roughly with the axis of rotation. Earth does not achieve that ideal perfectly, and neither do the other planets. But Neptune departs from it so strongly that its magnetism becomes one of the clearest signs that the hidden planet is stranger than the visible one. The magnetic field is tilted dramatically relative to the planet's spin, and it is also offset from the geometric centre as though the source region were displaced or the field itself distorted before it ever reaches space. This matters because a magnetic field is not only an invisible feature, it is a record of deep internal behaviour. It carries information outward from parts of the planet that no camera can see, and on Neptune that record suggests a world whose internal structure is organised in a way unlike the more familiar magnetic engines of Earth, Jupiter or Saturn. A planetary magnetic field is usually understood as the product of a dynamo, a process in which electrically conducting material moves within the interior and converts kinetic energy into magnetism. On Earth, the liquid iron outer core provides the conducting fluid, and convection combined with rotation helps sustain the field over time. Jupiter's immense field is also thought to arise from conductive material under extreme pressure, in that case associated with metallic hydrogen deep inside the giant planet. The general principle is not difficult to state. A planet needs conducting material, motion within that material, and a geometry that allows the resulting currents to organise into a long-lived global field. Neptune likely satisfies those broad requirements, but it seems to do so in an arrangement that differs sharply from the more centred and more orderly dynamos of some other worlds. The field Voyager measured was tilted by about 47 degrees relative to Neptune's rotation axis, a remarkably large angle, and the effective magnetic centre appeared offset by a substantial fraction of the planet's radius. That is not a small imperfection, it is a structural clue. If the source of Neptune's magnetic field sat deep at the centre, in a relatively symmetric layer, the resulting field would more likely resemble a simple dipole, somewhat like a bar magnet, even if not perfectly aligned. Neptune instead presents a field with stronger higher-order structure, meaning the magnetic geometry is more complex and irregular than a centered dipole alone would produce. The field changes more dramatically with position. Its asymmetry matters. It means that Neptune does not simply carry magnetism. It carries magnetism with a shape that has to be explained. Uranus offers an important comparison here because it exhibits a similarly odd magnetic geometry. Its field is also both strongly tilted and offset. That parallel is useful because it suggests Neptune's magnetic strangeness is not an isolated accident unique to one planet, but may be tied to the shared internal category of the ice giants. The obvious early temptation after Uranus was studied was to blame the magnetic oddity on Uranus's extreme axial tilt, as though the strange orientation of the whole planet had somehow twisted the field into an unusual position. Neptune complicated that idea immediately. Neptune does not rotate on its side. Its axial tilt is much more moderate, yet its magnetic field shows the same broad kind of displacement. That weakens any explanation based purely on the orientation of the planet as a whole, and shifts attention inward, toward the depth and shape of the conducting region where the dynamo operates. The most widely discussed interpretation is that Neptune's magnetic field is generated not deep in a compact central core, but in a shallower shell of electrically conducting fluid within the mantle. This possibility fits the broader understanding of Neptune's interior, where water, ammonia, and methane under immense pressure may enter unusual conductive states. If the dynamo operates in a shell rather than a central sphere, and if that shell is relatively thin compared with the planet's radius, the resulting field can become much less dipolar and much more susceptible to tilt and offset. In other words, the strange magnetic geometry may be telling astronomers that the dynamo region itself is shaped differently from the ones that power the more regular planetary fields. Neptune's magnetism may come from motion in a mantle layer rather than from a deep metallic core alone. That interpretation carries several implications at once. It links the magnetic field to the same exotic high-pressure interior chemistry that already helps explain the planet's heat flow and structure. It suggests that the mantle is not only convecting thermally, but also doing so in a way that supports electrical currents on a planetary scale. and it strengthens the idea that the ice giants cannot be understood merely as smaller versions of Jupiter and Saturn. Their interiors are organized differently enough that even their invisible architectures follow different rules. Neptune's field is therefore not just an oddity for specialists. It is one of the clearest indicators that the internal engine of the planet operates in an unfamiliar regime. The field also shapes the space around Neptune. Where a planet has a magnetic field, it carves out a magnetosphere, a region in which charged particles are guided and deflected by magnetic forces rather than moving freely as though the planet were absent. This interaction matters because the solar system is not empty between worlds. The Sun continuously releases charged particles in the solar wind, and when that stream encounters a planetary magnetic field, it is diverted, compressed, stretched, and restructured. At Earth, this produces a magnetosphere with a bow shock facing the Sun and a long tail extending away from it. Neptune has the same broad kind of magnetic shield, but because its field is so oddly oriented, the magnetosphere is more dynamically peculiar. As the planet rotates, the tilted field changes its presentation to the solar wind, almost as if the shield itself is wobbling through space. The resulting magnetic environment is not static. It is modulated by Neptune's rapid rotation and its field asymmetry, producing a system whose geometry changes in ways more pronounced than on planets with more centered fields. This dynamic magnetosphere helps explain why Neptune's auroras are also unusual. Aurora form when charged particles are guided by magnetic field lines into the atmosphere, where they collide with gases and transfer energy, producing emission on Earth. This process is concentrated mainly near the polar regions because the magnetic geometry channels particles toward high latitudes. Neptune does produce auroral phenomena, but not in the simple polar pattern one might first expect. Because the magnetic field is tilted and offset, the regions where particles are funneled into the atmosphere can occur far from the rotational poles, sometimes closer to mid-latitudes. The auroral behavior is therefore another outward expression of the deeper magnetic distortion. Even the sky glow of Neptune, faint and difficult to detect, follows the strange logic of the field rather than the simpler intuition of planetary symmetry. These auroras are also subdued by Neptune's immense distance from the Sun. The solar wind is weaker there than in the inner solar system, and the available charged particles are less energetically abundant in familiar terms. Yet the field still gathers and directs what does arrive, and the result is a quieter but scientifically revealing version of the same magnetic drama seen elsewhere. Neptune does not need bright auroral curtains to prove that its magnetosphere is active. The mere pattern of where the aurora appears already speaks volumes. It confirms that the field is not an abstract measurement detached from the planet's atmospheric life. It reaches upward, couples the deep interior to the upper atmosphere, and turns invisible geometry into observable consequence. There is something especially compelling about Neptune's magnetic field, because it is such a precise contradiction of visual expectation. The planet looks round, smooth, and calm from afar. A viewer unfamiliar with the measurements might assume a kind of global symmetry extends naturally from the blue disk inward. Instead, the field tells a different story. Beneath the apparent smoothness lies a conducting interior that does not generate a centered, orderly magnetism. The planet may be visually serene, but its invisible skeleton is skewed. Rotation, heat, and electrical conduction are producing a field that leans and shifts, shaping a magnetosphere that cannot be described as merely conventional. This is one more way Neptune resists becoming simple. Even the part of the planet no eye can see is arranged with a kind of measured imbalance, and that imbalance matters beyond magnetic theory. It reinforces the central lesson repeated across Neptune's atmosphere: storms and interior. The planet does not express its hidden structure in tidy ways. It is not only violent above the clouds, it is asymmetrical beneath them. The magnetic field does not settle the mystery of Neptune, but it sharpens it by adding another layer of evidence that the planet's deep interior remains incompletely understood. The atmosphere already hinted at a hidden engine. The internal heat strengthened that case. The magnetic field adds a final twist, showing that the engine is not only active, but geometrically strange. By the time the field reaches space and curves the paths of charged particles around the farthest major planet, it has already carried outward one of Neptune's most persistent messages. The deeper architecture is not where first expectations would place it, and the invisible world may be every bit as unruly as the storms above. The strangest part of Neptune's rings is not that they are faint, though they are, nor that they are dark, though they reflect very little sunlight compared with the brighter and more familiar rings of Saturn. The strangest part is that some portions of them appear to gather into arcs, dense clumps of material occupying only limited stretches of the ring, instead of spreading themselves evenly all the way around the planet. That should not be easy to sustain. A ring is usually understood as a system that smooths itself out over time. Countless particles orbit, collide, exchange momentum, and gradually distribute along shared paths, turning local irregularities into more uniform bands. Neptune, however, seems to preserve exceptions to that expectation. Its rings are not merely dim versions of the giant ring systems seen elsewhere. They are thin structures that combine fragility with persistence, delicacy with unexplained organization. In a planetary system already rich with atmospheric paradox, the rings add another quieter contradiction. Even the debris circling Neptune refuses to settle into the simplest possible form. For a long time, those rings were more rumour than certainty. Neptune lies so far from Earth, and the rings themselves are so dark and tenuous that direct observation was extremely difficult. Early hints came not from obvious imaging but from stellar occultations, moments when Neptune passed in front of a distant star and the star's light briefly dipped in suggestive ways. Those dimmings implied that something narrow and structured was orbiting the planet. Before Voyager 2 arrived, the interpretation was awkward because the evidence seemed to indicate incomplete ring segments rather than full continuous rings. That result was uncomfortable. Physics favoured continuous rings. Observation seemed to point toward broken ones. The flyby resolved part of the puzzle and deepened another part. Neptune did indeed possess a ring system made of continuous rings, but within one of those rings were brighter arcs, localized concentrations that preserved the earlier impression of incompleteness. The observations had not been wrong. They had merely glimpsed a structure more complicated than a uniform ring. The main named rings of Neptune lie close to the planet and are subtle enough that, against the blackness of space, and under the weak light available so far from the sun, they are almost ghost-like. The innermost is the Gala ring, broad and faint. Farther out lies the Leverrier ring, somewhat narrower and better defined. Beyond that sits the diffuse Lassell ring region, associated with nearby ring material including the Arago component. Outermost among the major named rings is the Adams ring, the one most closely tied to the famous arcs. These names, drawn from figures associated with the discovery and study of Neptune, give the system a kind of historical order. But the visual reality is much more fragile. Unlike Saturn's rings, which can dominate the appearance of the planet even from modest telescopes under good conditions, Neptune's rings do not advertise themselves. They exist near the threshold of easy detection, and their darkness is part of the reason. The particles appear rich in radiation-processed material and darker compounds, likely altered over time by impacts, sunlight, and charged particle interactions. They do not gleam, they absorb. This gives the entire ring system a muted character, as though the material orbiting Neptune has been aged into shadow. Yet the darkness does not mean insignificance. Ring systems are records of process. They preserve evidence of collisions, captures, breakups, and gravitational shaping. A ring is often temporary on cosmic timescales, an archive of violence translated into orbit. Neptune's rings almost certainly belong to that same logic. The material circling the planet is thought to be younger than Neptune itself in its current arrangement, replenished or reworked by past disruption. Small moons can be shattered by impacts. Tidal forces can tear weakened bodies apart if they cross too close to the planet. Dust and fragments can then spread into rings, while larger surviving moons sculpt the edges and maintain structure through gravitational interaction. Nothing about a ring system is static in the deepest sense. Even when it appears serene, it is the visible result of prior damage and ongoing correction. On Neptune, that quiet damage may be written most clearly in the Adam's ring and its arcs. The arcs bear names such as liberté, égalité, fraternité, and courage, labels that lend them an almost ceremonial dignity. But their scientific interest lies in the fact that they persist at all, left to themselves. Clumps inside a ring should smear out along the orbit through a process known as differential motion. Particles at slightly different distances from the planet travel at slightly different orbital speeds. Over time, any local concentration ought to spread. The arcs therefore require some kind of confinement, some mechanism that resists this natural tendency toward uniformity. The leading explanation involves gravitational resonances with nearby moons, especially the small inner moon Galatea. Resonance occurs when orbital periods line up in a repeating mathematical relationship, allowing gravitational nudges to accumulate at preferred locations. In principle, such resonances can trap material or maintain longitudinal structure, preventing the arcs from dispersing completely. This explanation is elegant and physically plausible, but the full behaviour of Neptune's arcs has remained difficult to model in perfect detail. They appear to evolve. Their brightness changes. Their exact structure shifts. The confinement works well enough to preserve the phenomenon, but not so simply that the mystery disappears. That balance between explanation and incompleteness is typical of Neptune. The broad mechanism may be visible. The exact arrangement still resists closure. The rings also reveal something about scale and fragility in the outer solar system. Neptune is a giant planet with a massive gravitational reach, yet its rings are narrow, dusty, and subdued rather than grandly expansive. They seem almost improvised compared with Saturn's luminous architecture. This does not make them lesser. It makes them more intimate as evidence. A faint ring demands a more careful reading because each part of it can be more sensitive to perturbation, replenishment, and loss. Dust can be eroded by radiation pressure and electromagnetic effects. Small moons can act as shepherds, confining ring edges or stirring material through repeated encounters. Collisions among particles can both spread and damp structure. The rings are therefore caught between forces that preserve them and forces that wear them down. Neptune's system appears to occupy that balance in a particularly delicate way. It is present, real, and persistent, but always close to the edge of invisibility and perhaps close to the edge of change. Several small inner moons orbit in and around the ring system, and their role is likely essential. Naiad, Thalassa, Despina, Galatea. And Larissa belong to a compact family near Neptune that interacts gravitationally with the ring region. Some of these moons may serve as shepherds, using their gravity to constrain ring particles into narrower distributions than would otherwise survive. Others may represent the surviving remnants of a once more disrupted inner system, bodies that endured while other material was reduced to debris. This is one reason Neptune's rings and moons cannot be treated as separate topics. They are parts of the same dynamical environment. A ring may be the memory of a moon. A moon may be the custodian of a ring. The boundary between object and aftermath is not always clean. That interdependence becomes even more suggestive when Triton enters the larger story. Triton, Neptune's great captured moon, likely did not form alongside the planet in the same orderly way that regular moons often do. Because Triton moves in a retrograde orbit, opposite the direction of Neptune's rotation and the probable original prograde motion of a primordial satellite system, its capture must have been a disruptive event. Once captured, Triton would have radically altered the gravitational environment around Neptune. Existing moons could have been destabilized, driven into collisions, or ejected. Over time, the modern inner system may have reassembled from the wreckage left behind by that ancient upheaval. If so, Neptune's rings may not be incidental decorations, but the surviving residue of a system once violently rearranged. The faintness of the rings would then match their history. They would not be primordial ornaments preserved unchanged since the birth of the planet, but later structures assembled from loss. Seen in that light, the arcs become even more intriguing. They are not simply odd lumps in a narrow ring. They may be temporary concentrations within a broader debris system, born from major gravitational trauma and then continuously sculpted by the surviving moons. Their persistence would represent not stability in the absolute sense, but a local victory of resonance and confinement over dispersion. This fits Neptune's larger identity unusually well. Again and again, the planet expresses order through imbalance rather than through simplicity. Its atmosphere is fast but unstable in detail. Its magnetic field is global but badly offset from symmetry. Its rings are continuous but refuse uniformity. The arcs are perhaps the purest expression of that pattern. They hold shape where shape should dissolve, but only partially, and perhaps only for as long as a delicate dynamical arrangement can endure. There is a visual poetry in Neptune's rings, though it is a restrained one. Saturn's rings dominate by brilliance and breadth. Neptune's rings whisper through darkness. They are difficult to see, narrow in scale, and marked by absences as much as presences. Yet this very subtlety gives them a different kind of power. They make the observer work harder, and in return they offer a more fragile mystery. Why do the arcs last? How stable are they across decades? What role do collisions, dust production, and shepherding moons really play? How much of the present system still carries the signature of Triton's ancient arrival? These are not questions about spectacle. They are questions about survival, confinement, and the long afterlife of disruption. By the end of the ring system, Neptune no longer appears as a planet encircled by simple debris. It appears as a world with broken light arranged into narrow structures that should be easier to erase than to preserve. The rings do not overwhelm the planet. They reveal it. They show that even in the cold darkness beyond easy observation, matter around Neptune has not spread itself into perfect obedience. Some of it still gathers, some of it still clings, and some of it remains where orbital logic says it should already have faded into uniformity. Triton moves the wrong way. That is the simplest and most revealing fact about Neptune's largest moon. While the regular moons of giant planets usually orbit in the same direction as the planet's rotation, following the broad inherited order of a system formed from the same circumplanetary material, Triton circles Neptune in retrograde, going against that expected flow. Its orbit is also inclined in a way that makes ordinary co-formation deeply unlikely. This is not the pattern of a moon that grew quietly beside its planet from the same local disk of gas and debris. It is the pattern of an intruder, an object that belonged elsewhere and was later taken in by Neptune's gravity. Once that becomes clear, Triton stops being merely the largest moon in the system and becomes something more consequential, a captured world whose arrival may have altered almost everything around it: Neptune's rings, its smaller moons. And perhaps even the present architecture of the system will begin to look different when seen under the shadow of Triton's capture. It is not simply another satellite. It is an event still preserved in orbital form. Triton is large enough that its capture could never have been a minor disturbance. It is slightly larger than Pluto, dense enough to suggest a mixed composition of rock and ice, and reflective enough to appear bright against the darkness of the outer solar system. Its surface, as seen by Voyager 2, carries an unusual beauty that seems almost too delicate for such a violent history. Pale terrain spreads beneath darker markings. There are smooth plains, fractured regions, ridged textures, and subtle colour differences that hint at active resurfacing in the past. Some areas bear the appearance of frozen flows, others the scars of older disruption. The surface does not look ancient in a simple, heavily cratered way, as though it has merely been left untouched for billions of years. It looks reworked, as if internal or seasonal processes have renewed parts of it. This gives Triton an identity beyond capture alone. It is not only dynamically unusual, it is geologically interesting in its own right. A cold moon that still shows signs of complexity. Voyager even observed dark plumes rising above the surface, evidence of active geyser-like behaviour, likely driven by seasonal sunlight, warming, volatile ices. That combination is part of what makes Triton so compelling. It is both a record of deep past disruption and a world that continued to evolve after the violence of its arrival. But the orbit remains the first decisive clue. A moon in retrograde around a giant planet cannot easily be explained as a native child of that planet's formation. The most plausible picture is that Triton was once an independent body, perhaps part of the same broader population of icy objects that includes Pluto and other large Kuiper Belt worlds. At some point in the early solar system, it passed close enough to Neptune to become trapped. Capture, however, is not a simple matter of drifting by and being seized. An object approaching a planet typically swings past and escapes again, unless energy is removed from the encounter. That means Triton's capture requires a mechanism. One widely discussed possibility is that Triton was once part of a binary system, two bodies orbiting one another while together travelling around the Sun. If such a binary passed close to Neptune, the gravitational interaction could have torn the pair apart. One object might have been ejected while Triton lost enough energy to remain bound to Neptune. This kind of exchange capture is dynamically plausible and fits the scale of the problem more naturally than simpler alternatives. Whatever the exact mechanism, the conclusion is the same. Triton did not always belong to Neptune, and when it arrived, it would have entered a system that was not prepared for it. That is where the true significance of Triton begins. A large captured moon on an initially eccentric and inclined orbit would have been a destructive presence. Before capture, Neptune may well have possessed a more orderly family of regular moons orbiting in the prograde direction, perhaps somewhat analogous to the compact satellite systems of the other giant planets. Triton's entry would have destabilized that arrangement dramatically. Gravitational interactions between a large retrograde newcomer and a pre-existing moon system would have excited eccentricities, altered inclinations, and driven collisions. Some native moons may have been flung outward or inward. Others may have smashed into one another, producing cascades of debris. Some may have been destroyed entirely. In this picture, the modern inner system of Neptune is not the calm survivor of primordial order, but the aftermath of a major reorganization. The rings, the small inner moons, and perhaps the loss of any earlier large regular satellites may all trace back to that era of upheaval. This idea helps explain why Neptune's present system can feel both organized and broken at once. The inner moons are there, but they are small. The rings are there, but they are faint and debris-like. Triton is there, but it moves opposite to the expected direction. Instead of one harmonious family formed together, Neptune seems to possess layers of history superimposed on one another. Triton represents the interruption. What came after had to reassemble around that fact. Over time, tidal forces between Neptune and Triton would have acted to alter the Moon's orbit, gradually circularizing it and bringing it closer to the more regular path seen today. But that process would not have been gentle for the rest of the system. During the long interval while Triton's orbit shrank and settled, its gravitational influence could have swept through regions occupied by earlier moons, continuously reshaping the available orbital space. A primordial system may have been ground down into debris and then partially rebuilt. The small inner moons observed today may be second-generation objects, formed from the disk of material produced after Triton's disruptive arrival. If so, Neptune's rings also become easier to understand, not as pristine leftovers from formation, but as fragments in a system repeatedly processed by collision and reaccumulation. Triton would then be the hidden cause behind much of Neptune's present modesty, in moons and delicacy and rings. It would explain why the planet seems to carry evidence of both order and damage at once. Triton itself remains caught in a long future shaped by tidal evolution, because it orbits Neptune in retrograde and lies within the synchronous radius. Tidal interactions do not slowly push it outward in the way Earth's tides are carrying the Moon away. Instead, Triton is expected to spiral inward over immense timescales. That future is far beyond human timescales of observation, but its logic is clear. The orbit is not the final equilibrium of the system. Neptune still holds a moon that is gradually losing orbital energy. If enough time passes, Triton may one day cross the region where tidal forces exceed its structural strength and be torn apart, potentially forming a far more substantial ring system around Neptune than the faint one now seen. That possibility gives Triton's story an unusual symmetry. A captured moon may have helped create the debris and rings of Neptune's inner system in the past, and the same moon may one day become debris itself. The intruder that reshaped the system could eventually be reduced by the same gravitational authority it once challenged. Yet for now, Triton remains intact, and what a world it is. Its surface temperature is among the coldest measured anywhere in the solar system. Nitrogen ice coats much of the terrain. The tenuous atmosphere, thin and fragile, rises from seasonal sublimation of frozen volatiles. The observed plumes suggest active transport of material, whether powered by sunlight-penetrating translucent nitrogen ice or by other shallow subsurface processes. The surface is young in places, implying resurfacing over geological time. There are cantaloupe-like terrains unlike anything seen elsewhere, smooth plains that may once have flowed, and fractures hinting at internal stress. Triton therefore broadens Neptune's mystery in two directions at once. Dynamically, it is a captured body that destabilized a planetary system. Geologically, it is an active, icy world still doing strange things under faint sunlight. The two aspects belong together. A body large enough to rewrite Neptune's satellite history is also large enough to remain internally and seasonally complex. That dual role gives Triton unusual narrative weight. It is not just one more moon orbiting an already interesting planet. It is the moon that changed the terms of what Neptune became. This may be why Triton feels less like a satellite and more like a rival presence. It carries enough mass to dominate the moon system. It likely arrived from elsewhere. It may have erased much of what came before. It possesses its own atmosphere, its own active surface, and its own long-term tidal fate. Around many planets, moons help complete the story of the primary world. Around Neptune, Triton partially rewrites it. The planet's rings make more sense because Triton exists. The compact inner moons may exist in their present form because Triton arrived. The outward appearance of Neptune's satellite family, sparse in large regular companions yet rich in signs of disruption, looks less like a quiet inheritance and more like a reconstruction after capture. Everything observed so far fits into a coherent history, but not yet a settled one, because the exact sequence of destruction, debris formation, and reassembly remains only partly recoverable. What remains clear is the scale of the intervention. Neptune did not simply acquire a moon. It acquired a foreign world large enough to reorganize its entire surrounding system, and the consequences of that ancient capture still circle the planet today. Far beyond Neptune's cloud tops and well outside the faint ring system, the planet's authority continues into a region of space so large that its outer moons seem less like close companions and more like distant objects temporarily gathered under one blue sovereign. This is the realm where Neptune's gravity competes not only with the motion of individual satellites, but with the larger pull of the Sun itself. Every planet occupies a zone within which its gravity can hold moons in stable orbit, a region known as the Hill Sphere, and for Neptune that zone is immense. The reason is not that Neptune is the most massive planet, because it is not, but that it resides so far from the Sun that solar interference is weakened considerably by the time it reaches this outer frontier. Distance, which elsewhere makes Neptune seem diminished, here gives it reach. The same remoteness that leaves the planet under thin sunlight also allows it to govern a vast surrounding volume of space. That wider kingdom matters because it helps explain why Neptune's moon system is not merely compact and regular near the planet, but scattered, irregular, and historically layered far beyond it. The farther one moves from Neptune, the less the moon system looks like a neat family formed in one place, and the more it resembles a collection shaped by capture, collision, and survival. The innermost moons belong to a different order. Close to Neptune are small regular satellites whose orbits are relatively circular and lie near the planet's equatorial plane. These are the moons most closely tied to the ring region and to the present orderly architecture of the inner system. Naiad, Thalassa, Despina, Galatea, Larissa, and Hippocamp occupy this compact inner realm, and their significance is greater than their size might suggest. Some help shape the rings gravitationally. Some may preserve traces of earlier disruption in their orbital relationships. Hippocamp in particular is so small and so near the path of the larger moon Proteus that it has invited the suggestion that it could be a fragment born from an ancient impact on its larger neighbour. If so, even the tiny inner moons are not merely leftovers from formation, but products of later damage and reassembly. Neptune's inner system therefore appears orderly in the present tense, while still carrying the memory of collision in its details. This pattern repeats across the planet's wider family. The second largest moon, Proteus, stands out because it is large enough that simple intuition might expect it to have settled into a more perfect spherical form. Instead, it remains irregular, its shape still marked by the fact that gravity has not fully forced it into a smooth hydrostatic balance. That alone gives Proteus a rough, incomplete quality, as though it occupies an intermediate state between the largest rounded worlds and the smaller battered bodies that never become fully self-shaped. Its surface is deeply cratered, and the enormous crater Pharos dominates one hemisphere with a scale that hints at how close the moon may have come to catastrophic disruption. A collision large enough to excavate such a feature without destroying the moon altogether suggests a history balanced on the edge between survival and fragmentation. That matters because Proteus may help illustrate how Neptune's moons persist in a system where impacts and rearrangement have long been important. It is not simply a second moon after Triton, it is a damaged survivor. Nereid belongs to another category entirely, discovered long before many of the smaller moons were known, It circles Neptune on a highly eccentric orbit, one of the most elongated among the larger planetary satellites in the solar system. That eccentricity immediately sets it apart from regular moons that formed in a settled circumplanetary disk. Nereid seems to inhabit a middle ground between native order and outer irregularity, and for that reason it has often been treated as a clue to an earlier phase of Neptune's dynamical upheaval. One possibility is that Nereid was once part of a more regular satellite system, but had its orbit drastically disturbed during Triton's capture and the subsequent reorganization of Neptune's surroundings. Another is that it belongs to a more complicated history of partial capture or scattering. Either way, Nereid feels transitional. It is too odd to belong comfortably to the innermost regular group and too substantial to disappear into the swarm of smaller, distant irregulars. In a system already shaped by intrusion, Nereid looks like a moon whose orbit still carries the scars of historical dislocation. Beyond that lies the outer population, and here Neptune's kingdom becomes truly diffuse. These distant moons do not move along the same calm patterns as the inner satellites. Their orbits are often highly inclined, highly eccentric, and in several cases retrograde. They are small, faint, and difficult to detect, which is one reason so many were found only in the modern era of larger telescopes and sensitive imaging. Their very existence implies that Neptune's gravitational influence reaches astonishingly far into surrounding space. But their orbital character implies something equally important. Many of them were probably not formed in place. They are captured objects, or at least the products of capture-related fragmentation. Bodies that once moved through the outer solar system more freely before becoming bound to Neptune. In this outer domain, Neptune looks less like a planet surrounded by children of its own formation, and more like a collector of passers-by. Moons such as Halimede, Sao, Laomedea, and Samatha belong to this irregular class, each moving on broad, inclined paths that speak of dynamical history rather than calm origin. Neso, the outermost currently known moon, is especially revealing because its orbit reaches so far from Neptune that it takes many years to complete a single circuit. At that distance, a moon no longer feels like a close satellite in the everyday imagination. It feels almost like a small neighbouring world being kept only loosely within Neptune's larger domain, and yet that loose grip is real. Neptune holds it because the Sun, though still dominant overall, is no longer able to strip everything away in that remote region. The existence of such far-flung moons turns the outer edge of Neptune's system into a kind of threshold between planetary control and solar freedom. It is one of the clearest demonstrations that a planet can possess influence far beyond what its visible disk suggests. The irregular moons also hint at family relationships of their own. Some appear to cluster in orbital properties, suggesting that they may not all be independent captures, but fragments of once larger parent bodies broken apart after capture. This is an important distinction. A moon system can grow not only by acquiring new objects, but by shattering acquired objects into smaller related groups. In that sense, Neptune's outer kingdom may preserve another level of damage, one in which capture is followed by fragmentation and fragmentation by long orbital survival. Halimede and Nereid, for example, have invited discussion because of similarities in surface colour and the possibility of some historical connection, though whether one is a fragment of the other or both descend from a common ancestor remains uncertain. What matters most is the larger implication. Neptune's outer moon system is not just a set of isolated points. It may be a genealogy of breakups, each irregular orbit carrying not only the memory of capture but perhaps the memory of later collision as well. This makes Neptune's moon family unusually expressive of the outer solar system as a whole. The inner moons record proximity, shepherding, and second-generation rebuilding near the rings. Triton records large-scale capture and system-wide disruption. Nereid records orbital disturbance on a grand but incomplete scale. The far irregulars record the planet's ability to seize and retain small bodies from the broader trans-Neptunian environment. Taken together, they form less a tidy ladder of satellites than a layered archive of gravitational history. That is why the Moon system matters beyond simple enumeration. Each region around Neptune tells a different part of the same story. Near the planet, gravity organizes debris into rings and small moons. Farther out, it preserves survivors and anomalies. At the widest scale, it reaches into a large hill sphere and turns distant objects into reluctant members of a planetary retinue. The result is a family whose variety is itself the evidence. Few planetary systems show so clearly how formation, capture, collision, and long-term orbital selection can coexist within one domain. Neptune's distant moons also force a more careful understanding of what a moon really is. The word can imply intimacy, as though satellites are naturally close companions circling just beyond the visible limb of their planet. Neptune challenges that image. Some of its moons are so remote that their paths stretch deep into space, occupying regions where the difference between satellite and small captured body becomes almost philosophical. They remain moons because Neptune's gravity still closes their orbit, but they do so while inhabiting a scale more often associated with heliocentric distance than with local companionship. This broadens Neptune's character in a subtle but important way. The planet is not only violent in atmosphere and strange in magnetism, it is territorially expansive. Its power extends into a wide outer court of small worlds, some orderly, some battered, some almost certainly foreign in origin. By the time the eye moves from the rings to Proteus, from Nereid to the irregular outer moons, Neptune no longer appears as a solitary blue sphere with a few attendants. It appears as the centre of a gravitational province, one in which closeness and distance, origin and capture, survival and breakage all remain visible at once. The Moon system does not merely orbit Neptune. It explains the scale on which Neptune acts. It shows that even at the edge of the major planets, where sunlight has thinned and human observation grows difficult, the farthest giant still commands a domain large enough to gather debris, preserve intruders, and hold a scattered kingdom together against the wider pull of the sun. The most violent world in the solar system does not announce itself with size alone, with brightness alone, or with the kind of visual drama that first overwhelms the eye. Neptune is not the largest planet. It is not the brightest. It does not carry the broad luminous rings of Saturn, the immense visible mass of Jupiter, or the easy familiarity of worlds long known to human sky-watching. It is distant, difficult to see, and often introduced as the outermost major planet, almost as though remoteness were its defining trait. But distance is only the opening condition. What makes Neptune unforgettable is the way that nearly every deeper look has forced a correction of first expectations. A planet so far from the sun ought to feel close to exhaustion, governed mainly by cold, weak light and slow decline. Instead, it reveals an atmosphere of astonishing speed, storms of planetary scale, a heat budget not fully matched by solar input, a magnetic field that refuses central alignment, rings that preserve improbable arcs, and a moon system shaped by capture and damage. Neptune is not merely far away. It is a world in which almost every major system carries some form of tension between what should be simple and what is actually observed. That is why the planet lingers in planetary science with unusual force. It is not only interesting in pieces, it is coherent in its defiance. The paradox begins with energy. Sunlight at Neptune is weak, reduced by vast distance into something thin compared with the force that warms and structures the inner planets. The upper atmosphere is bitterly cold. The year is immensely long. Seasons unfold across spans of time so broad that human observation has covered only a narrow portion of the full climatic cycle since the planet was discovered. On paper, these facts seem to lead toward restraint. They suggest a world in which weather should be present only in subdued form, where atmospheric contrasts would be shallow and movement slow. Yet Neptune overturns that expectation at its most visible level. The winds are the fastest known on any major planet. The atmosphere organizes itself into broad jets, dark vortices, and bright high clouds. Storms emerge with enormous scale and then disappear again, not because the climate is weak, but because it is dynamic enough to create large coherent disturbances without preserving them indefinitely. Violence on Neptune is not the violence of a single permanent monument. It is the violence of a system that keeps finding ways to renew motion under improbable conditions. That fact alone would make Neptune a serious puzzle. Combined with everything else, it becomes the center of the planet's identity. Internal heat appears to be one of the main reasons that puzzle remains physically plausible at all. Neptune radiates more energy than it receives from the Sun, which means the visible weather above is almost certainly being fed from below, as well as modulated from above. This is where the planet ceases to be just a cold sphere in dim sunlight, and becomes a thermally active world wrapped in deep blue atmosphere. Beneath the clouds lies a hot, dense mantle rich in water, ammonia, and methane under extreme pressure, and beneath that a still denser core. The materials there do not behave in familiar ways. Molecules are compressed into exotic states. Carbon chemistry may enter regimes where diamond formation becomes possible. Water-rich matter may become electrically conductive under conditions almost absent from ordinary terrestrial experience. The precise details remain modelled rather than directly observed, but the larger conclusion is already powerful. Neptune's meteorology is not a thin surface response to weak solar forcing. It is the atmospheric expression of a hidden interior that has not finished releasing its energy. The farthest giant is not running on leftovers alone. It is still giving off more of itself than distance would seem to allow. That hidden energy also helps explain why Neptune and Uranus, though similar in size, composition, and basic classification, behave so differently. The comparison between the two is one of the strongest pieces of evidence in Neptune's favour as a truly distinctive world. Uranus, slightly closer to the Sun, might have been expected to show equal or greater atmospheric vigour. Instead, Neptune repeatedly outperforms it in visible activity. The contrast suggests that planetary character depends not only on what a world is made of, but on how effectively it can transport internal heat into the atmosphere. Uranus may have lost or trapped its available heat through a disrupted internal history. Neptune seems to have preserved a more accessible engine. This does more than explain a difference between neighbouring planets. It changes the way the ice giants are understood as a class. They are not interchangeable blue outer worlds. They are experiments in divergent thermal evolution. And Neptune stands out as the one whose interior still asserts itself most clearly into weather. Even the magnetic field carries that same pattern of hidden disturbance. A simple planet, at least by first expectation, might produce a magnetic geometry roughly aligned with its spin and centered in its bulk. Neptune does not. Its field is strongly tilted and offset, likely generated in a conducting shell within the mantle, rather than in a compact central core alone. The resulting magnetosphere is correspondingly strange, and the auroral behaviour in the upper atmosphere follows that strange geometry rather than a neat polar symmetry. Here again the visible planet turns out to be a misleading guide to the structure within. The blue disk suggests smoothness. The magnetic field implies an interior with a symmetry built into its workings. Neptune therefore becomes more than a world with unusual weather. It becomes a world whose invisible architecture is itself displaced from ordinary planetary expectation. The ring system and moon family continue the same theme in quieter form. Neptune's rings are faint, dark, and narrow, yet within them some arcs remain clumped where orbital reasoning says they should disperse. The likely explanation involves resonance and confinement, probably with small nearby moons, but the full structure still resists simple closure. The rings look delicate because they are. They may also be the residue of ancient disruption. Then comes Triton, the captured moon that orbits in retrograde and therefore almost certainly did not form alongside Neptune in the ordinary way. Triton turns the entire satellite system into a historical reconstruction. Its arrival likely destabilized and perhaps destroyed an earlier family of moons, contributing to the creation of debris, rings, and second-generation satellites. Farther out still, Neptune's kingdom extends into a wide hill sphere populated by irregular moons whose distant, inclined, and eccentric orbits speak of capture and fragmentation rather than calm inheritance. The planet's gravitational family is therefore not a simple household. It is an archive of intrusion, breakage, and long survival. That matters because it widens the meaning of Neptune's violence. The violence is not limited to meteorology. It appears in system history, in orbital capture, in the reassembly of a moon system after disruption, and perhaps one day in Triton's own eventual inward destruction if tidal evolution continues far enough into the future. What gives Neptune its particular scientific power is that none of these facts stand alone. The fast winds are more interesting because they occur under weak sunlight. The storms are more interesting because they are unstable rather than permanent. The internal heat is more interesting because a neighbouring planet lacks a comparable atmospheric response. The magnetic field is more interesting because it suggests deep structure, unlike that of better-known dynamos. The rings are more interesting because they are both fragile and organised. Triton is more interesting because it is not simply large, but foreign. Each feature deepens the others. The result is a planet whose mystery does not depend on ignorance alone. Neptune is not compelling merely because so much remains unknown. It is compelling because what is already known does not collapse into a single tidy picture. The evidence is rich, but the synthesis remains incomplete. That is a more durable form of mystery than simple absence. There is also the observational challenge. Neptune has been visited closely only once. Much of its history has been pieced together from telescopic monitoring, spectroscopy, infrared mapping, and long gaps between decisive glimpses. Storms can appear and vanish between generations of instruments. Seasonal changes unfold over spans longer than many careers. The deep interior remains accessible only by inference. This means Neptune is not merely a world with unanswered questions. It is a world that is difficult to interrogate properly. The slowness of its seasons, the remoteness of its orbit, and the rarity of close exploration all conspire to keep the planet partially withheld. Yet what has already been learned is enough to make one point with unusual clarity. Neptune is not the quiet terminus of the solar system. It is one of its most dynamically expressive worlds, a place where cold does not eliminate motion, where distance does not suppress structure, and where hidden energy continues to rise through the blue. In that sense, Neptune's deeper significance extends beyond its own orbit. It changes how outer planets are imagined, how ice giant interiors are modelled, how atmosphere and interior are linked, and how planetary systems remember violence long after the original event has passed. It also hints at the importance of similar worlds around other stars, because ice giants may be common in planetary systems, even when the solar system offers only two nearby examples. To understand Neptune is therefore to understand more than one distant planet. It is to confront an entire category of worlds through one particularly forceful case. And Neptune, by every indication so far, is the forceful one. It is the farthest major planet, but distance is not its final meaning. the final meaning is harder and more interesting than that. Neptune is violent not in spite of its remoteness, but through a combination of remoteness, hidden heat, unstable structure, and long unfinished history. Everything observed so far can be arranged into a plausible story, but not yet into a settled one. And that unresolved difference is exactly what keeps the planet alive in science, a cold blue world at the edge of sunlight, still moving too fast, still hiding too much, and still refusing to become simple. The farther a world is from easy understanding, the more tempting it becomes to reduce it to a simple image. Neptune has often been reduced that way, to a distant blue sphere at the edge of the planetary family, cold, dim, and somehow secondary to the larger giants closer in. But that impression never survives careful attention for long. Again and again, Neptune proves to be a world where weak sunlight does not mean weak motion, where hidden heat matters more than first appearances allow, and where even the invisible structures of the planet carry an unusual tilt, offset, or instability. Its storms do not last forever, yet the atmosphere remains powerful. Its rings are faint, yet they hold stubborn irregularities. Its greatest moon does not belong to the quiet logic of native formation, but to capture and upheaval. Even the planet's first discovery came not through direct sight, but through the trace of an unseen influence acting across space. In that sense, Neptune has always existed slightly beyond the obvious, first as a gravitational disturbance, then as a remote disk, and finally as a world whose deeper character only grew stranger as more was learned. That may be the most enduring quality of all. The planet does not become less mysterious as the evidence improves. It becomes more precisely mysterious. The outlines sharpen, the mechanisms become clearer, and yet the whole still refuses to collapse into something ordinary. Neptune remains a place where atmosphere, interior, magnetism, rings, and moons all seem to carry the signature of a system not fully settled, a world still shaped by buried energy and unfinished explanation. And so it lingers at the edge of the solar system not as a quiet endpoint, but as one of its most restless and elegant unanswered places, blue in appearance, violent in behaviour, and still holding more of itself in reserve than human observation has yet been able to bring fully into the light.